Okay, so we're going to look at a couple more slightly more awkward examples of this reverse chain rule for integrating. In example 10, we've got a fraction, and it's got a cosec squared and a cot in it. And this from the formula book is telling us that cot differentiates to cosec squared, or negative cosec squared. So it feels to me like this is going to be a useful tool. What we have in addition is that we've got the cot is on the bottom of a fraction, is in the denominator, with a cubed in. So we're probably looking at y equals this denominator, 2 plus cot x to a power. This power is negative 3. So I probably need it to be negative 2, so that when I differentiate and I raise the power, I end up with negative, and drop the power, sorry, I end up with negative 3. So this is my guess. There'll be some coefficients to play around with, but we'll have a look at that. So dy by dx is going to look like the derivative of the inside, which we know is negative cosec squared, straight from the formula book, multiplied by negative 2 lots of 2 plus cot x to the negative 3. So this is looking fairly close. It's quite encouraging. The two negative signs cancel each other out. So I end up with 2 cosec squared x times by 2 plus cot x to the negative 3, which is almost identical to our integral. It's just that it's got this 2 in here instead. So what I need to do is I need to go back and amend that by just halving, and then this, that will just divide it by 2. So I end up with cosec squared times by 2 plus cot x to the negative 3, which is exactly what this is. And what that tells me is that the integral of cosec squared over 2 plus cot x cubed is this. It's a half of 2 plus cot x to the minus 2 plus our constant for integration, because we're dealing with an indefinite integral. So again, it's just noticing that there's a derivative in there somewhere and thinking about what that's going to look like in terms of the chain rule. And for our final example, we have another awkward trig function. It's 5 tan x sec to the power 4x. And on the surface, there are two possible strategies here, because tan differentiates to sec squared, which looks really familiar actually, because we've got a tan and a power sec. And sec differentiates to sec tan. But what we need to remember is that for the chain rule to work, I need a function to a power, and then I need to differentiate this. And that's what brings the derivative of that function outside and lowers the power. So the tan isn't going to work as my function because it doesn't have the power. There's no way I can differentiate tan on its own without a power and end up with sec to the power 4. However, if I say y equals sec x to a power, I can get sec to a power back out and then some tans in there. The question is what my power should be. Now ordinarily we'd go 1 up and we'd do 5 because that 5 will lower down to 4 when I do my differentiating. But because the derivative of sec contains another sec, differentiating this will bring the power down to 4, but then multiply it by sec again, so bring it back up to 5. So power 5 isn't going to help us. I need the power to actually match in this instance, because I get a sec back again from when I differentiate. So dy by dx is going to be the derivative of sec, which is going to be sec x tan x, multiplied by 4 lots of sec x cubed. Just applying normal chain rule. But then we can tidy this up. This is going to give us 4 tan x and then sec to to the power 4x. And you can see this is really, really close to our integral. The only difference is that's a 5 and that's a 4. How do I turn a 5 into a 4? Well, I multiply it by 5/4, because that will clear the 4 out and bring a 5 in. So I've solved that first part of the problem. The integral of 5 tan x sec to the power 4x is just 5/4 of sec to the power 4x. But I've got a definite integral here, so I'm doing it between 0 and theta. I don't need a constant. But the question doesn't tell me to find the integral. It tells me the integral is equal to 15/4, find theta. So we don't actually know what the values are that we're integrating between, but we do know that the answer is 15/4. So we've got a little bit more work to do here just to tidy this up. So what we're going to do is we're going to say, right, well, that means that 5/4 of sec 4 theta take away 5/4 of sec 4 0 equals 15/4. Remembering, of course, that sec x is 1 over cos x. Cos of 0 is 1, so that means this whole thing becomes 1, because 1 over 1 is 1, and 1 to the power 4 is still 1. So I have 5/4 of sec to the power 4 theta minus 5/4 equals 15/4. I can add 5/4 to both sides. And then I can tidy up. If I multiply by 4 and divide by 5, I end up with the much tidier sec to the power 4 theta equals 4. I'm not quite finished because I need to unwind that and get the exact value. And it does say exact value. So I need to take, so sec theta is the 4th root of 4. Now the 4th root of 4, it's not immediately obvious, I guess, but it's going to be root 2. Because if I square root 2, I get 2, and if I square that again, I get 4, 4th root of 4. What is quite interesting about this particular question is you need to be able to sort that out yourself. Because if I type into my calculator the 4th root of 4, it will tell me 1.4142, which is root 2, but it's the decimal approximation of root 2. As we've met in a couple of other places in this unit, the calculator is good, but it's not perfect and it can't maintain exact values for everything. So you need to be able to pull this apart yourself. And if it says exact and you plug it in a calculator and get 1.41, you either need to know that that's root 2 or you need to back up and do it by hand, because that's not going to give you the marks for this question. Final little thing. This is sec theta is root 2. Well, that means that cos theta is 1 over root 2 because it's the reciprocal. And if you remember it, that's great. If you don't remember it, I can just inverse cos of 1 over root 2. And in this case, it will give me the exact answer because it's doing a fairly simple unwinding of a trig thing. So theta must be 1/4 of pi. It's quite involved. There's a lot going on. The real trick to this one, though, is just spotting right at the beginning that I can use sec differentiates to sec tan, and that therefore my original function must be sec to the power 4. As with a lot of stuff that involves trig, really this is about practice in order to recognize these things more easily.